Hello everyone! In this video, I'm going to be covering how to convert repeating decimals to fractions in different ways, like using an infinite geometric series. After that, we will prove that 0.9 repeating equals 1. The main reason I chose to make this video was because I thought it would be a fun video to make, and I wanted to explore Manim, the animation software 3Blue 1Brown uses for his videos. Alright, so first, what is the definition of a repeating decimal? Well, one example of a repeating decimal is 0.3333 repeated. The 3 repeats and goes on forever, so instead of writing the whole thing, we can represent it with a dash on top of the number. We can represent this more formally by using a sigma sign. X sub n is defined by this sigma with the index of I equals 1 and the stopping point of n. This, however, is only the partial sum since it stops at sum n. We want an infinite sum since there are an infinite number of 3's in 0.3 repeated. So we can replace the n with infinity. Now, if we start with I equals 1 and plug it into the element, we get 3 over 10. Then, when I equals 2, we get 3 over 100, and we add 3 over 10 and 3 over 100, and so on. How do we solve this sum? How about other repeating decimals, such as 0.218 repeated? Let's start with the basics. A geometric sequence, geometric progression, is simply a sequence of numbers where each term is the previous term multiplied by a common ratio. One example of a geometric series is 2, 4, 8, 16, 32. The common ratio is 2, as each term is being multiplied by 2 each time. The common ratio cannot be equal to 0, or else all the terms would be 0. Let's represent a geometric sequence in a more algebraic way. As the first term is a and the common ratio is r, then we have the geometric sequence a, ar squared, ar cubed, ar to the power 4, and so on. We can represent the last term of the sequence as ar to the power the number of terms minus 1. So in this case, there are 5 terms, and 5 minus 1 equals 4. So the last term is ar to the power 4. Now that we know what geometric sequences are, before we get to the sum of an infinite geometric sequence, we should figure out the sum of n terms of a geometric sequence. Let's say S sub n is the sum of a geometric sequence. So it would be a plus ar squared plus ar cubed and so on plus ar to the power n minus 1. Now let us multiply this sum by r. R times S sub n would essentially increase the exponent of r on each term by 1. And we know this by using the laws of exponents. A to the power m times a to the power n is a to the power quantity m plus n. So, for the first term a, we can represent it in terms of r by saying it is a to r to the power 0, instead of just a. Then, since we are multiplying by r to the power 1, that term would change to ar. The same is the case for the last term. We just add 1 to the exponent n minus 1, and we get n. So the last term's exponent would be n. And we can replace r to the power 4 with r to the power n minus 3, since there are 7 terms. Now that we have these two sequences, we can subtract them. Almost everything cancels out. ar squared, ar cubed, ar to the power n minus 3, ar to the power n minus 2, ar to the power n minus 1. And the only ones left are a and ar to the power n. So, on the left side we have S sub n minus r times S sub n, which can be factored to S sub n times 1 minus r. And for the right side, since a and ar to the power n are left, it would be a minus ar to the power n. We can divide by 1 minus r on both sides to find s sub n only. But we can only do this when r is not equal to 1, since we cannot divide by 0. We are left with s sub n is equal to a minus ar to the power n divided by 1 minus r, when r is not equal to 1. Then we can just factor out the a in the numerator to simplify it further. If r is equal to 1, though, each term would just be a, and the sum would be the number of terms times a, which is n times a. Okay, now that we've figured out the sum of n terms of a geometric sequence, let's figure out the sum of an infinite geometric sequence, which will help us convert repeating decimals into fractions. An algebraic way to find the formula of the sum of an infinite geometric series is to take the limit as n goes to infinity of the formula we just looked at. So we would have the limit as n goes to infinity of the sum of the nth term of a geometric sequence. Let's isolate the r to the power n first, since we are finding the limit as n goes to infinity, and r to the power n is the only part of the expression that has n in it. If the common ratio, or r, is greater than 1, then as the exponent goes to infinity, it would keep increasing and diverges to positive infinity. On the other hand, if it was less than or equal to 1, then it would oscillate. When n is odd, it would be negative, and when n is even, it would be positive, and it does not converge to anything. Well, what if r is greater than -1 and less than 1, like a half? Well, the value would keep on reducing to 0 as n increases, as we can see from this animation, so it converges to 0 as n approaches infinity. Negative a half fits in the range too, you may be asking. So what about negative a half? Wouldn't it oscillate since it switches between even and odd numbers? Well, if we look at the animation, we can see that both the negative and positive values get very close to 0 compared to when the common ratio was -2. We can also look at this visually on Desmos. So we can conclude that r to the power n equals 0 when r is greater than -1 and less than 1. Using this fact to solve the limit of this expression, we can substitute r to the power n with 0, which would give us a over 1 minus r when r is greater than -1 and less than 1. So this is our formula for finding the sum of an infinite geometric series. Let's have a look at a geometric proof instead, which assumes that the sum converges. We have a right triangle and a square that looks like this. Let's say each side length of the square is a. We can represent the top side length as a minus ar plus ar, which is just the same as a. Then we can have ar plus ar squared plus ar cubed and so on until infinity, which if you just flip it represents a geometric sequence, as we have mentioned before. We can call this our sum. Now we can determine that the green triangle and that the inverted orange triangle are similar. This is because these two vertical angles are equal. And this red triangle and this orange triangle here, which means that these other two angles, this one and this other one in the red triangle, are also equal. So, from the AA similarity theorem, the orange and green triangles are similar. From this, we can have the equation s over a equals a over a minus ar. To simplify this, we would multiply both sides by a and then just factor out the a from the denominator. Then we just cancel the a's and are left with s equals a over 1 minus r, which is just the same result we got when we solved it algebraically. Now that we've proven the sum of an infinite geometric series formula in two different ways, let's use this formula to convert repeating decimals into fractions. Now we have arrived at the main part of this video, converting repeating decimals to fractions. Let's look at our previous example, 0.3 repeated, and convert it to a repeating decimal using an infinite geometric sequence first. We know it is just 3 over 10 plus 3 over 100 plus 3 over 1000 and so on. And to find it, we would need to use the formula s equals a over 1 minus r, where a is the first term and r is a common ratio. The first term in this case is 3 over 10, and 1 over 10 is the common ratio. Plugging it in, we would get 3 over 10 over 1 minus 1 over 10, which simplifies to 3 over 9. So, 0.3 repeated equals 3 over 9. Let's try converting another one with an infinite geometric series, like 0.218 repeated. That would be 0.2 plus 0.018 plus 0.00018 and so on, which is just 2 over 10 plus 18 over 1000 and so on. In this case, we would take the infinite sum of 18 over 1000 plus 18 over 100,000 and so on and add it to 2 over 10. The first term is 18 over 1000 and the common ratio is 1 over 100. So we would have 18 over 1000 divided by 1 minus 1 over 100, which is equal to 18 over 990. We can simplify this to 1 over 55. This is the fraction for 0.18 repeated, but since we are converting 0.218 repeated, we would have to add 0.2, or 2 over 10. Adding 2 over 10 plus 1 over 55, the LCM is 110, so we get 24 over 110, which, when we divide the numerator and the denominator by 2, we get 12 over 55, which is our answer. Now, with all this computation involved, it is very easy to make a silly mistake here and there. So, let's look at another way to convert repeating decimals into fractions, which is less of a formal way to do it. Let x be equal to 0.218 repeated. If we multiply this by 100, that would move the decimal point 2 to the right, which would leave us with 100x equals 21.818 repeated. Now we can subtract them to get rid of the 0.18 repeating. 21.8 minus 0.2 equals 21.6. So therefore, 100x minus x equals 21.6. From this, we can subtract 100x minus x, which would give us 99x equals 21.6. And finally, x equals 21.6 over 99. However, we want a fraction with the numerator and the denominator being integers, so we can multiply both by 10, which moves the decimal point 1 to the right. This leaves us with 216 over 990. We can simplify this further by dividing the numerator and the denominator by 18, which would give us 12 over 55 as our final answer, which is what we got with an infinite series as well. But how do we determine what to multiply by? Well, if there's one decimal repeating, multiply it by 10. If there are two decimals repeating, like in this case, multiply it by 100. And so on, you get the idea. Let's try another one of our previous examples. Let x be equal to 0.3 repeated. Since there is only one decimal repeating in this case, we multiply by 10. So it would be 10x equals 3.3 repeated. Then we subtract these two, which gives us 10x minus x equals 3, and the 0.3 cancels out. So we have x equals 3 over 9 as our final answer. Or we can simplify this further to simply 1 over 3. To finish off the video, here is a quick proof that 0.9 repeated equals 1. Let's prove this statement using an infinite geometric series and the definition of a repeated decimal. Let x sub n be 0.9 plus 0.09 plus 0.009 and so on. Using our knowledge on the sum of an infinite geometric series, we would need the first term and the common ratio to be able to solve this. Let's write the first term, which is a, as 9 over 10. The common ratio is just 9 over 100 divided by 9 over 10, which is just 9 over 100 times 10 over 9, which is 1 over 10. Now, we can just use the s equals a over 1 minus r formula we have explored it in previous parts of this video. Plugging it in, we would get s equals 9 over 10, which is a, over 1 minus r, which is 1 over 10. Solving this, we would get 9 over 10, and the denominator would be 10 over 10 minus 1 over 10, which equals 9 over 10. Now you have 9 over 10 as the numerator and 9 over 10 as the denominator. So, this would equal 1. Therefore, 0.9 repeated equals 1.